Good morning, ladies and gentlemen.
Good morning.
Welcome back to our third meteorological virtual series. We are leveraging on the new normal to expand the scope of understanding of atmospheric sciences within the tropics or globally, and to have a fair idea about a new trend in the atmospheric sciences. Today, we will have presentation from Dr. Alexander Roberts from University of Leeds. I will call upon Professor Danoa to give us a brief background of the program and introduce the speaker as well. Thank you very much. Prof.
Yes, okay. Thank you very much, Mr. Bashir. Thank you very much. I'm really honored to be asked to chair this morning's function. So greetings to all the participants who have joined us for this third seminar. In fact, this seminar series has been instituted by the Ghana Meteorological Agency, GMET, and the Kwame Nkrumah University of Science and Technology to strengthen our collaboration as far as climate, environment, and all other issues related to climate sciences are concerned. And also to build the capacity of the two institutions in training our younger generation of early career scientists. This seminar series is actually within the Fund African Science for Weather Information and Forecasting Technique project, with the main coordinating institution at the University of Leeds in the UK. So these two institutions have been working together, and we feel that we should do something that will be a legacy. And this seminar series is actually one of them. We intend to let it be sustained. And maybe, who knows, it can develop into other beneficial areas of cooperation. So for today, the third seminar series is going to be delivered by Dr. Alexander Roberts, and I'm just going to give a brief of his profile. Dr. Alexander Roberts is a research fellow. His areas of expertise are convective storms, African meteorology, mesoscale dynamics, numerical weather prediction, nowcasting, atmospheric mineral dust, reanalysis, and so forth. And he's a postdoctoral researcher for climate and atmospheric science at the University of Leeds. He's currently working on the West African Monsoon Multiscale Analysis Project, which is actually called SWAMA, the SWAMA project for short, in which he carries out the dynamics of the West African monsoon in the Met Office Unified Model. Prior to this, he worked towards his PhD investigating mesoscale convective systems over West Africa close to the monsoon front. This included simulations using the weather research to forecast the GCRF model. So, ladies and gentlemen, we welcome Dr. Alexander Roberts.
Can you see my screen in presentation mode now? I've got a BSc in Meteorology from the University of Leeds, and then a PhD in my first postdoctoral position. We're both studying dust storms in West Africa, particularly connectively produced dust storms off boobs. So this is what this image down here is. And now I'm employed on the SWIFT project as the satellite and nowcasting postdoc. So the GCRF SWIFT project so SWIFT stands for Science for Weather Information and Techniques. It's a £9 million consortium project funded by the Global Challenges Research Fund. Within that, we have got connections between, so it's led by NCAS and the University of Leeds, but then there's partner institutions across the UK and Africa. So there's 4 partner countries in Africa. So that's Senegal, Ghana, Nigeria and Kenya, and within each of those partner countries we're partnered with both the National Met Service and also a research institution, so the university that does research into climate and weather. So the project structure is, broadly speaking, split into 3 different strands. So the first strand is kind of focused on users and evaluation. Strand 2 is the science strand. So this looks at forecasting on a range of different timescales, from kind of very short hour timescales up to kind of seasonal and sub-seasonal forecasting. And strand 3 is the cross-cutting activities. So this is training, test beds, management and legacy. Personally, I'm focused heavily on the remote sensing and navigation side of the science, and I also have responsibilities in terms of training the test beds, both participating in them and also kind of helping to organise them, and also working with legacy. So I'm going to be talking today about nowcasting specifically, and nowcasting for Africa. So I want to try and keep this at quite an introductory level. So I'm going to start off with kind of what is nowcasting, and specifically what is it when we're talking about Africa. Why is it important? Why do we need now? And then a little bit about the nowcasting technologies and specific approaches that we believe would be helpful for use in Africa. I'm going to go through a little bit of the recent progress that we've had as part of the SWIFT project, and then just to talk a little bit about some of the challenges that we see kind of coming on the horizon and possible ways that we can solve these problems. So, what is nowcasting? So, nowcasting, by the WMO, is the detailed description of current weather along with forecasts obtained by extrapolation from a period of 0 to 6 hours. But really, what does this actually mean? Because although it's quite clear, it's also, there's a lot of room for interpretation in there. Also, that time frame we don't believe is necessarily strictly kind of useful. So, in a recent paper that's just been published, that I was the lead author on, we have actually produced a definition for what we believe African nowcasting should be. And this has got 3 key elements to it, and then several other features that we believe are typical for nowcasting, and that we think should be kind of be focused on in terms of nowcasting in Africa. So the first of these key points is that there should be analysis of near real-time observations. So in most nowcasting systems, really we're talking about remote sensing, so either rainfall radar or the use of satellite data. But as long as this is near real time and you can get the data to be delivered quickly, it can also be augmented with in situ instrumentation data, and even observer reporting is a helpful thing to include as well. The second key component of nowcasting really is the forward propagation of identified important features. So this example here on the left is from the German National Weather Service nowcasting system called Nowcasting, and what they've done is identified features using rainfall radar that they are important, and then have tracked these in time, and then this produces these kind of risk envelopes, these regions where these storms are going to present risk in the near future. And the other kind of method that you can use for this is to kind of, the third key element is that nowcasting requires continued monitoring. If you have nowcasting shifts that are limited in time and only kind of really check up, so you need people to be actually aware of the current situation pretty much all the time and updating this, so that if anything changes and you need to issue warning, then typically as well, nowcasting's also applied to high impact weather, so we're talking in particular in the tropics. Scale convective systems is really what we're kind of focusing on. And so heavy rainfall, strong winds. So this image here on the left is, I think, flooding in Accra, and on the right this is actually damage to the airport in Senegal that occurred when there was a very strong storm that produced very strong downdraft winds, and that caused a large amount of damage to a very new airport. The other thing that is typical is that you have to focus this very short-term forecast in poor weather, in high-impact weather, but then you can also consider stakeholders that are vulnerable to that to be kind of, so aviation is a really good example for nowcasting. So although the risk of a plane being severely impacted by high impact weather such as these circumvention systems is fairly low, because actions taken to avoid that, the potential for catastrophic problems is still there, and so you would really want to make sure that nowcasting for aviation is performed, and actually across Africa that is the case. And there's also other industry that would be important to consider in this as well. Another feature that nowcasting typically has, although it's not strictly necessarily true, is that it's usually forecast on fairly localized forecast domains. Part of this is it makes it easier for you to be able to perform your nowcasting, but also in the past this is partially partially driven by the fact that rainfall radars, which lots of nowcasting kind of originated from, have a limited region which they can cover, and so you would have these positioned in key locations that would give you the ability to predict on a short time scale when high impact weather was going to hit a target that you were concerned about it reaching. And a bit now, that's kind of the timescale issue that we've mentioned at the beginning. So we believe that nowcasting shouldn't typically be defined on a strict timescale. And to kind of explain this, this graph is quite useful. So on this axis here, we've got the quality of the forecast against lead time, and so this bottom line here gives an indication of the skill of the forecast for numerical weather prediction, and then this other line coming down here indicates the skill of the forecast for nowcasting. So essentially at the beginning we're talking about an observation, so we've got very high skill, and then that drops off very quickly. And the region where this crosses over indicates the point at which the skip nowcast is below the skill of the NWP forecast. And so this really gives you an indication of the useful timescale for nowcasting. And you can see here that this is crossing at approximately 6 hours in this case. But what we know about NWP is that the skill of forecast produced by it vary quite significantly. So in a particular region, the skill of your NWP forecast, which actually then change the point at which these two lines cross. The same is the case for the skill of your nowcasting. So certain conditions might mean that your nowcasts are performing well for hours, whereas other conditions might mean that your nowcasts aren't performing well for very long at all. So really having a strict timescale on this isn't ideal, and so we need to kind of let forecasters use their judgment in when they believe that they should be using NWP over nowcasting type extrapolation. And the other thing that is also very typical of nowcasting systems is that, so it's sort of twofold here. So the first one is automated processing of data. So both getting your observations and model data into a system together and kind of automating all the features that are going on, so you're not having to actually have any sort of manual input there, and then producing a visualization for the human forecaster to be able to identify regions at risk, where the high impact weather is, and how this might need to be converted into a warning to be issued. But also having a person there means that you're able to identify spurious non-physical features. So if you can see that your system has produced something that doesn't make sense physically, then that warning doesn't get issued automatically. But then the other feature of this is that everything has to be done rapidly, in near real time. You can't have a system that relies on the gathering of lots of observations from around the country that take days to arrive, because then by the time you produce your nowcast, it's out of date and that's worthless.
Sure.
Similarly, if you don't have a means of dissemination of your warnings, observations all the way through to dissemination has to be done very rapidly and efficiently. So why do we actually need nowcasting? Hopefully you should be able to see why there is value in it already, but I'll try and explain a little bit. So the first thing to consider is that differing forecasting timescales require different approaches. So we know that if we're talking about forecasting for days, kind of out to weeks or almost, then we're looking at numerical weather prediction models. We're looking at synoptic scale features that we think that the model has a good chance of being able to capture that variability and do a good job of predicting it. However, if we're talking about individual convective systems, there's no way that we'd be trusting people doing that. And also there are limitations on how well your NWP can produce this latency. So not only do you have to have time to run the model, you also need to have processing time, which takes quite a while, or you might have a step that you need to consider in your model where for the first few hours of the simulation you don't believe what it's saying. And to fill that sort of gap and also have data arriving all the time, not just in kind of these discrete blocks in terms of initiation times for a model, really we use nowcasting type products for that. So here it's labelled as satellite, but on radar as well, and that's something that we need to fill that time scale that we otherwise wouldn't be able to produce forecasts for. The other consideration is that different forecasting techniques aren't necessarily available to everyone. So I'll go back to this schematic here, except for I'll just change it to a slightly different version. And so now instead of having a single NWP skill line, we've split it up into a synoptic scale. So consider this to be simulations that are, say, global simulations like GFS, things like that, that they've got a fairly coarse grid. They don't have, they're not convection permitting, so they've got parameterized convection, and generally we wouldn't be able to consider them to be capable of representing kind of the complexity of mesoscale convective systems, say. Then we've moved on to kind of a mesoscale NWP model, so this is more like your kind of WRF or Cosmo that you'd be running on a limited area. You have a high grid resolution, you could choose the microphysics that you're using, and you have a better idea of the dynamics that the model might be able to represent. And this would do a better job on these shorter timescales and would give you higher skill for systems that would be producing your high impact weather. And then we've still got our nowcasting line, which is basically an observation early on, but then decays fairly quickly with skill with time as the extrapolation becomes less useful. And so you would, in this case, consider these crossing points to be the important points in terms of where we can consider our highest skill lies. So nowcasting on the short term, absolutely the case, even in places that have got advanced mesoscale NWP type models being run every day. Nowcasting is an important thing for those functions to do. But in reality, there's lots of places around the world where this type of simulation isn't easy to come by and isn't easy to produce. I mean, from our experience in Swift, that actually running with this type of model is difficult because we've got a situation where in order to run a high skill model, you probably need a large amount of computing power. You need skills that are quite difficult to attain sometimes. If you've got a small number of people that actually know how to run this type of model, and then some of them leave to go work elsewhere, then you've lost those skills fairly easily, and there's a certain vulnerability into this. And it's not unusual to have a national Met Service that relies almost solely on NWP and satellite data for their forecasting. And so it means that this sort of nowcasting extrapolation technique becomes more important because you don't have this in between kind of mesoscale high resolution NWP to rely on for that little bit. But another important consideration is that means that nowcasting is important is kind of the regional variations in the type of weather that occurs. So if we look at this on a kind of global or continental scale, so this in the top right is a similarly chart from the UK Met Office that shows, basically this is a lot of kind of what is used for producing forecasts in the UK to a large extent. And the important features on here are generally isobars and fronts. So the isobars give you information about the pressure, but it's generally the wind speed and wind direction that we're interested in. And the fronts give you an indication of cloud and the likelihood of rainfall. This type of forecasting relies heavily on models, and actually nowcasting is probably secondary in terms of importance, because the high impact weather that we get in the UK is far more likely to be driven by frontal systems than it is by the convective systems or organised convection. Whereas if we go to the tropics, actually the cause of high impact weather there is mainly driven by mesoscale convective systems. They produce the most rainfall, they produce very heavy rainfall that can cause floods, there's lightning, there's hail, there's very strong winds associated with them. I mean, these are the feature that we really care about the most in lots of different ways. And actually, although we might have information in terms of equatorial waves or features that might encourage the production of convective rainfall that we might be represented in a model, actually, in terms of the specifics of what the storm is doing and how it's developing and how that might impact people on the ground, really, a nowcasting approach is far more suitable for that. And so, regionally, we get these differences in suitability for nowcasting or the need for nowcasting. And then the last one of these points is that not only have we got regional variations in the type of meteorology that would make nowcasting more or less important, but we also have regional variations in vulnerability. So not only do we have differences in terms of vulnerability between, say, countries in the mid-latitudes and the tropics because of socioeconomic issues, but even within countries we've got different levels of vulnerability associated with, say, a rural or an urban environment where the level of rainfall in one place might lead to flooding and it doesn't in another. And so we need to be aware of that on a local scale in order to be able to understand how to really kind of use warnings from the nowcast data that we've got. So I'm just going to give a very brief overview of the kind of nowcasting technology that's available, but with a little bit of a focus on what we believe in SWIFT to be kind of a most useful approach for Africa. So, kind of traditional nowcasting in the US, Europe, places like that, rainfall radar systems are kind of the thing that is most used. And they've existed since the 1950s, they've been widespread since the 1970s, and you kind of see, even without an added layer of software to do extrapolations and additional analysis, that actually seeing what's happening in near real time on a rainfall radar is very useful to give you the ability to predict warnings on short time scales. However, in Africa, rainfall radars aren't widespread. Even successful deployments of systems, so the South African Weather Service has a network of rainfall radars. We know that these systems are difficult to maintain, they're very expensive. There are many cases where rainfall radar systems have been installed, have been operational, and then when there are issues and it breaks down, it becomes something that is very difficult to get fixed. And even if it is fixed, it then breaks down again. And then if you've spent a large amount of money getting it fixed the first time, is it worthwhile spending the money to get it fixed again? So what's the solution to this? We've already probably mentioned it, is we believe that the use of geostationary meteorological satellite data. So Meteosat is the satellite that we're talking about. It's been through several generations. We're currently on the second generation. The third generation will be coming soon. It has high temporal resolution, It's Pan-African coverage, so wherever you are on the continent, this is a tool that is useful. It's currently got spectrum of 12 wavelengths. The images that you would receive from your system would be approximately 15 minutes latency at that stage. So you can see these convective systems on these kind of images very easily, and you can really do some very kind of good things in terms of nowcasting with this sort of data without ever needing to have the expensive rainfall data. The other advantage is most of the required hardware for a national net service in Africa is in place for this, and therefore it is relatively low cost. The Nowcasting Africa service is broadly used across national net services in Africa. Satellite data is being received like daily, all the time. It's every 15 minutes, more images are coming through, and it avoids lots of limitations that other solutions kind of present, such as unreliable internet connection or slow internet speeds, because this is a satellite link. Also, the quality of the data that's coming through is kind of like we go over. There's not just satellite data, there's other model data and other things that are ready to augment that. So in terms of potential for nowcasting data, the use of severely metered data is kind of what we consider to be the best option. So once you've got hold of your data, kind of what do you do with it then? So you could just view the images and make your predictions based on that. But actually, there are lots of systems out there that do kind of additional processing that enable more kind of information to be gleaned from just those images. So there's a couple of examples here. So this is a really simple one. So this is a tiny Rainfall system. This is radar, reflectivity, and there's an automated. This is just an example of one of the products that are available from the software. So cloud type, which gives you information about kind of cloud height, cloud depth, how cold the cloud tops are. And it's very easy to quickly just look at this and see where your regions of kind of mesoscope convective systems are likely to be. So NWCSAF is the Nowcasting Satellite Application Facility. It's one of a number of 8 SAFs, which are, so they're supported by UMETSAT. And basically the idea is that these different application facilities are out there to make the best use of the satellite data that's being produced. So the NWCSAF is for making the best use of satellite data for new weather prediction, and the NWCSAF is there to make use of satellite data for nowcasting. So it's to provide national meteorological services with an advanced, robust and reliable systems to support both operational and research activities in nowcasting. I'm just going to give a few examples of some of the products that are available. So convective rainfall rate is one of the ones that is most used from our experience and people find most useful. And you can see quite easily how this is taken in satellite data and also used in NWP, you know, if they're using GFS. And it produces this image that gives you an idea of not only which cells or which storms are likely to be producing the most rainfall, but also kind of give you the regions within the systems that are likely to be producing the most rainfall. The other most widely used product from NWCSAF, from our experience, is the rapidly developing Thunderstorms product. So this uses satellite data to identify storm regions and creates these kind of individual cells that are regions of interest. It categorizes them based on whether they're triggering, growing, mature or decaying, and also gives information about the intensity, which is indicated by the thickness of this outline, and the direction of the storm, and kind of what that predicted motion is in the next 30 or so minutes. Other products that are available from NWCSAF include wind speed, so these are based on cloud motion vectors, information about cloud top heights and temperatures, cloud type, which is what I showed before, but also cloud microphysics, precipitation, so chance of precipitation, also kind of intensity of precipitation, the likelihood of convective initiation, various stability indices, things like total cold water vapor, but also another feature that we think is really important here is the extrapolation of imagery. So basically, a standard nowcasting technique is this forward extrapolation in time of imagery. So you can do this manually, sort of just by looking at the images, and you can see, say, this is the storm that we're interested in here, and it's moving, and you can see the changing of its shape. And you can also think about this in a way of, like, if you have these images from the recent past, you could create an animation. So say we're interested in producing a nowcast for Conakry in Guinea, and we can see that this large MCS system is approaching, and we've also got these small systems here. So we might be issuing warnings for these in the short term, but also be aware that there is this large MCS system here that is heading in the direction that we're interested in. So based on the size and speed of the storm as it is at the moment, you would kind of calculate how quickly it's going, how long it's going to likely to take for it to reach there. You might say approximately 6 hours time, we'd expect this storm to reach Conakry. In reality, it's like 8 hours. So I mean, it's not a bad guess, it's a really good prediction. And even though there is a disparity there between what you predict based on the current storm speed and just using that in the future, you would be updating it in the interim. So you'd be constantly monitoring this system, and if it slows down, you'd be able to adjust your warnings or adjust your forecast based on that. But then obviously there are tools for automated extrapolation. So the one that's included within NWCSAF is the extrapolated imagery product, so that's EXIM. And so here's an example. This on the left here is the observations for this period that we're looking at. And you can see that there's a system of interior that's moving to the west, and you would be able to give a fairly reasonable expectation that this is going to produce a rainfall. On the right here, only the first image is observation, or the convective rainfall rate product based on observations. Every other frame here is extrapolated imagery that uses the cloud motion vectors and model information to determine the location of that storm that's been observed in the first frame. And you can see that actually storm speed is modelled quite fairly well, and if you were using this to give you a warning of what was likely to be hit in the near future, in reality, storms don't shrink as they dissipate. What they tend to do is fragment and break up. And so because the extrapolation will just take what's there and continue to move it forward, it won't reduce those storms in size or dissipate in any way. So storms in the extrapolations will persist beyond their lifetime that we see in observations. And because of this, we can see here, so just looking at the red and the dashed yellow lines, this is the time of day and the rainfall rate. And we can see that while the 90-minute extrapolation matches the observed convective rainfall rate for some of the day, actually for most of the time it exceeds it, and we're getting more rainfall being predicted in the extrapolations than we have in the actual product. But we understand why that is, and actually it's still a useful thing to have. So a little bit about the recent progress within SWIFT. So as I mentioned before, the current situation in at least the SWIFT partner countries is that nowcasting is fairly limited to aviation. So this is using satellite imagery to kind of understand where the risk features are, so where the storms are, and being able to guide flight paths around that and to avoid people trying to land planes when the conditions are very poor at airports. There are no widespread radar networks, and there is actually no widespread use of automated nowcasting systems. certainly not in the SWIFT partner countries. I know in South Africa, NWC SAF is used. So SWIFT's nowcasting efforts, just briefly, is we've installed a C-band satellite antenna at Chilbottom in the UK. We are now receiving the Nowcasting For Africa service, which is the same as what the National Met Services in Africa receive. NWC SAF is running operationally. We've now actually got a second system to act as a failover if we have problems, because we've had various issues in Chilbottom, and now that it's difficult to travel to fix the equipment, it's becoming even more complicated. And the images are generated, and then so we're receiving the data, we're processing it at Chilbottom, we're moving it to Leeds by the internet, and then making it accessible on our online catalogue. So we've got several domains over different parts of Africa that are focused on the SWIFT partner countries. And it means that we've got access to NWC SAF products for operational nowcasting, and we're trying to do this all the time, and it's been running since March 2019 now, so I think we've been fairly successful in doing that. Other recent progress, so African receiving stations already exist within the national Met centres, that SWIFT has been involved in the purchase of additional processing equipment to allow for nowcasting to take place alongside the more traditional forecasting approaches that have already been taking place in the national Met centres. We've also supplied the 4 partner universities that we're working with receiving and processing equipment, and hope that within these institutions this equipment will be used to receive data that can be used for research, but then also students that are being educated in using this equipment and software will then be familiar with it if they then go to work in the national Met. And we can see here, this is an image of the KNUST where the dish is being sold. Other progresses, we've tried to build quite a lot of training into the programme of SWIFT. So in 2019, we had an NWC SAF installation and training class that we delivered at the SWIFT Summer School at KNUST. We're providing ongoing support for the partner countries that are involved. We've got a training website that gives hardware specifications, guidance, and a few little walkthroughs on how to actually set up both the hardware and the software. Another big step forward that we see is the use of test beds. So the SWIFT test beds have and will continue. So later this year there's a test bed, another test bed coming up, to bring together researchers and forecasters from across Africa and the UK to get them into the same place. Well, physically it was, but probably not. In the near future, it'll be virtual, to get us to kind of be able to communicate with each other, share experiences, share understanding. So the Senegalese and Nigerian Met Services, AMASIM and NIMET, are also on track to be running NWC SAF operationally using their data that they get through their UMETCAS system, hopefully before the end of the year. ACMAD are also running NWC SAF operationally already. Continued legacy of different institutions in Africa working together and helping to build on what's occurred so far within SWIFT. But one of the real issues here is scaling. So at the moment, nowcasting activities happen routinely, but they are for aviation. And in order for this to be scaled up and to broaden the availability of nowcasting, there has to be a switch to automated techniques. It's not possible to continue to use manual nowcasting techniques and also have coverage over large different regions and have different considerations for different industries and things like this. And hopefully, really, this move towards automation and to more wide-scale use of nowcasting techniques will allow different industries. So, for example, the energy industry, so not only oil, but also the renewable energy sector will benefit greatly from access to nowcasting warnings. Agriculture and shipping, regions, sorry, these are kind of industries that would really find this information useful. If only for logistical purposes of knowing whether or not you should be trying to dry your cocoa at a particular day or time of day, if you know something's on the horizon coming. And hopefully, the way that we see this going is that there'll be growth in the production of nowcasting and the operational kind of nowcasting, and it could lead to commercial opportunities opening up. And you can see how these industries are high value and they have a lot of money, and if it would save them money to be able to have these warnings, they would pay for them. And so we hope that this scaling allows this to occur. In terms of technology, we see that we do understand kind of how projects in the past have produced nowcasting solutions for different places in Africa. There's been a big focus on Lake Victoria. But all those systems have sort of failed, and they've worked well scientifically, they've been verified, they've been tested, and they do work. But after the end of the project, the support stopped. And so we understand that using a system that is already in place, and we see South Africa is not linked to the SWIFT project. After the end of the SWIFT project, the products will continue to be developed. They will continue to provide support for users. We really see that. Also, we've tried to put a lot in training materials, and all the documentation that we're providing is going to be available beyond the project as well. And hopefully as well, the structure of NCAS means that there will be people that are still maintaining the UK-based setup, and that will persist well beyond the end of the project too. Another major concern was the new generation of Meteosat. So the Meteosat third generation, is still a lot of uncertainty about how this will affect the Nowcast. And I think what we're concerned about is the ability to generate NWCSat products in the country. And so we're really working hard to ensure that there's a continuity of service there. There is a lot of potential because the new instrumentation on the Meteosat satellite would allow for much better nowcasting to be performed, so especially things like the lightning sensor. But if it comes at the cost of not being able to produce products in country, then that isn't particularly helpful. Other things that we are aware of as issues is there's this gap between the data being available and also being able to visualise it a lot. And so it's just working with the UK Map Office in the development of a tool called Forest. So it's a data agnostic visualisation tool. So it's able to open different either model data and show things side by side, and we've been working with them, and actually NWCSat products are now integrated into that, so then you can open them. They have to be available locally, so the production of the products has to be done locally, but now we've got to a stage where they are able to be visualised within Forest. We've also worked on the development of Bark, which is a plugin for Forest that allows for annotation and report making within that Forest system. So we really hope that this will be developed in the future by the Met Office and will become a tool that is available. It is really helpful for not only just producing nowcasts, but longer term forecasts as well. And then also this step at the end in terms of dissemination, we're aware that is something that's vector and raster format that then can be overlaid on the map. And there is another element to the FASTER project that is also the development of a mobile application to enable nowcasting products to be disseminated to users directly. What we really envisage being the value to this is that if the API allows access easily to these products quickly, then National Meteorological Services could generate warnings and then use this data in their own dissemination to, like if they have an app, to actually push warnings to people. So now just a quick roundup of stuff I've talked about. So Nowcasting Africa is currently largely limited to aviation safety. There is definitely a greater need for satellite nowcasting. Rainfall radars aren't widespread. There's a great need for high-skill, short-term predictions that aren't available through NWP. African weather lends itself to this approach because of the complexity and the chaotic nature of mesoscale convective systems. And there's definitely a need to provide warnings to either vulnerable or industrial kind of sectors that I think would potentially open up the commercial avenues. We know that satellite nowcasting systems already exist and are well developed and are supported, but they're underutilised. So this is something that we're trying to address in SWIFT, and we've been working with our African institutions to kind of understand the barriers to using this, and also been trying to do as much training and providing as much support as we can to make this a step forward that doesn't then disappear at the end of the project. And we've made quite a lot of progress, but we also feel that there's more to be made, and hopefully in the long term we see that this will help to reduce the exposure to weather risks for individuals, companies and governments. Essentially, we do want to kind of reduce the vulnerability across all these timescales, and I think that's difficult, but it's the target. That's what we want to try and do. Yeah. Thank you very much for listening. And, I welcome any questions. Thank you.
Wow. Thank you very much, Dr. Alex, for a wonderful presentation. It's time for, we've learned a lot. It's time for Q&A. So you can raise your hand for questions.
Hello. I think before we take the first question, there's an input here in the chat. It says your NWP skills profile peaks much larger than in the case of the UK. Is it that because of the model you use, or is to do with the climate of Africa?
So the images that I showed were basically just illustratory schematics. I think the points that I was making still stand. I think having a timescale applied to nowcasting just doesn't make sense. And also, if you've got access to high-skill NWP, then great, but nowcasting is still important on very short timescales. If you don't, then nowcasting becomes important beyond those times.
Good afternoon. Can I ask a question?
Yes. Yes.
Good afternoon. My name is Estelle de Koning. I work for WMO, and I'm the head of the World Weather Research Program. And of course, Alex, I'm quite aware of the work that you've done, and thank you for excellent work and excellent presentation. I think it was really capturing all the real important projects and all the important points, the challenges, and the many intricacies of doing nowcasting in the African continent. I think SWIFT has made fantastic progress, and I think you should just be applauded for everything that you've put in place and made operational and available to this community. One question I have is, I see that you make mention of forest and that this will at some point be a very nice display tool. So my question, the first part of the question is, when is this? Is this 5 months away or years away? But you don't have to answer that. And then the other one would be, I mean, if you supply an image of, for instance, the CRR or the RDP to the African continent, I saw that you have different windows, West Africa, East Africa, and also the High Africa. I think it would be important to be able to have like a zoom feature that somebody can zoom in to see more details, because if you see these very small, polygons over a huge area, the only way to see whether it's approaching your city or, your sports stadium or your airport would be to have a bit of detail on what looked at. I'm asking the question because I know in South Africa, and I think Monet Gibbon is online, did this display on Google Maps in the background, and then one can zoom in and you can have like, it's approaching this, I say, sports stadium where there's a big event, or it's approaching, it's a big hailstorm and you have to warn the city because there are lots of cars standing outside that can be damaged or something like that. So that is my question about the display. So first of all, when can we see this forest? Because I know it was also discussed in the context of the highway project. And then does it have a zoom feature?
So forest, I don't know. My involvement with forest has been, I've kind of on the edges, I've been aware that this development has been going on. Has been more to do with the bark side of things, which was the plugin for forest, which is to do with annotation and report making. So that means you can draw on and kind of decide what your important features are and highlight them, and then write kind of text beside and then link it to things. So I mean that's the side of it that I've been involved with. Forest as a whole, I don't know. It keeps going through various incarnations, and every time it gets better. And actually, at the moment, I think there is a development of Forest Lite, which is something that is specifically designed for use on systems on local data. Because I think the original idea behind Forest is that it uses data that's stored remotely, and you access that, and then it gives you the image back. And obviously, if you've got internet connectivity issues, then that would be no good. So really what you need is something that works on a local client and accesses the data that you've got access to. So I'm sorry, I can't answer when, I'm afraid. I think development is still actively going on. It's still a priority, and hopefully there'll be testing. I know that there's plans to be kind of testing associated with the WCSSP Southeast Asia work. So I have high hopes, but I'm sorry, I don't know the time frame for it. In terms of Zoom, I'm aware that what I said conflicts with what we've done. So I said about kind of having these localized domains that we can produce nowcasts for a very specific region, and that is true, and I definitely stand by that. But what we did was we covered a large area using NWCSAP, and then produced images that then are very easy to zoom in on a very specific location. So in answer to that, we are in the process of, so we're going to try and use the faster API, so that would be RDT and convective rainfall rate, and then produce zoomable maps that will be available on the SWIFT Nowcasting catalog. We're also in the process of updating the Nowcasting catalog so that it should also allow us to put images side by side that would be useful. So not just Nowcasting products, but also most recent GFS sort of imagery of things like Cape, instability. So we want to kind of update all of this, and it is in the pipeline. At the moment, though, you're right, we do not have a zoomable function, and we need one, and that is, I think, a very key thing to be able to do if you are following there, because you need to be focused
no,
on.
I appreciate your answer. I mean, these things are on the table, and none of it is easy. I saw that Javier Valverde online, he's from the Nowcasting set, based in Spain. So I guess they will be really, really happy to see what a great utilization you've made of the Nowcasting set products. And I can only congratulate you on that. Thank you so much.
Yeah, I just feel that it makes absolute sense to use it because it is so well developed in terms of the number of products that are available, the support that's available.
Exactly.
Prof. Lamte, your question. Can you please ask a question?
Nice. I was wondering if you could comment on other methods of nowcasting. I think Netflix and Sweden or Norway also uses other methods. I don't know if you can comment on that in comparison with NWC.
So yeah, I see Netflix is, I don't know if people know what Netflix is. Netflix is a project that's run by CEH in the UK, and it's partnered with Anas in Senegal. And the idea behind that is to use a statistical approach to kind of give risk for the likelihood of high impact weather on the very short term, and also translate that all the way through to kind of flood risk. And Netflix has been very successful, and I see that as being an approach that could be very successful elsewhere in Africa. The problem is at the moment it's focused specifically on Senegal and Dakar, and you would need to do the same method over every region of interest that you have. At the moment that hasn't happened, I'm not saying it won't happen, but I think the NWCSAF approach is certainly a more general answer to the question. But no, I think the stuff that NFLIX is doing is great. It's really interesting and useful.
Thank you very much. Rita Roberts, can you please ask your question? Your hand is up.
Yes, hi. Thank you. Thank you, Alexander, for a very illuminating, great presentation on the nowcasting challenges. My name's Rita Roberts. I'm from the National Center for Atmospheric Research in the U.S. And I have been involved recently with Estelle and others on the highway project in East Africa for Lake Victoria. So my comments, a couple of comments, and just one question is that in the East African project for Lake Victoria, of course there too is the real challenges of getting data in real time at forecast offices for the forecasters to provide the type of warnings needed. But what was actually a really key outcome from the highway project was the facilitating workshops where forecasters came together with the end users. And so the end users in this case were lake community advocates and all the players you need, not just to do the nowcasting, but also to get the information out to the end user in a way that they can use it. And so I see in the SWIFT project that you've been doing really substantial training of the forecasters, which is just terrific. It wasn't clear to me how much SWIFT was pulling in the various end users, like those on the oil rigs or those who were doing the agricultural farming. And so that's one question for you. And then the other question is, in the Lake Victoria project, what also became a significant outcome was that forecasters were disseminating information to the end users on WhatsApp.
Not to be too prescriptive. So I don't know if maybe I was unclear before, but when I was saying about other projects have made these really kind of fantastic steps forward, and then beyond the end of the project, they've not been used. I was specifically thinking about, so I know there's development, like the work by Thierry that used storms over land near Lake Victoria to predict storms over the lake overnight, and that relied on a certain specific data file that was being generated by someone at NASA that then stopped after a certain period of time, and people weren't using this system because they said that the overheads in terms of doing the processing on these files and the downloading of the data was just too much. And so it's very successful and it works very well, but actually if it's not usable in that sense, then it's kind of, I feel bad saying failed, but it's failed in what it tried to do. And another example is the UK Met Office had a project that the way in which the dissemination was done for these warnings was by giving mobile phones to people. And that's not a sustainable thing. you can't expect to have a project that does this and it be a one-time thing, that it's got finite funding to do it, and then that is the solution, because you're not going to continue to be able to provide this stuff. So the way that we're trying to do it is to come at it from several different angles, but also have to leave the flexibility there. So part of the nowcasting faster APIs we want to produce is to have this ability to generate products, make them available in a format that is very quick to download. It doesn't take a large amount of bandwidth, but it gives the flexibility there for National Met Services to produce their own forecast and to disseminate it in whatever way they choose to. So whether that's via WhatsApp, then that'd be great. But also there's a potential there for us to have this data being freely available, and commercial companies could either access it and produce things. And I think it's about making sure that there's several options there. So initially for FASTA we're talking about making an app, and that would be very successful possibly if we got word out and it was a good kind of use of the data and it was coded well. But having both the option of an app there, but also the back end all being sorted and then the data just being available. That is kind of, we're trying to cover several different bases here. And I think flexibility is key to this in part.
Yeah, I would just jump in here and say that's fine. I'm not saying that WhatsApp is the application for any specific place. As I mentioned, radio broadcasters, journalists, all disseminating too. So it sounds great that you're pursuing. For each region, there may be different
Absolutely.
needs. Thanks.
Samuel, can you ask a question?
Yeah, thank you. Thank you, Dr. Roberts, for the wonderful presentation. Yeah, my question is, you know, it's well known that weather dynamics within the mid-latitudes is controlled by frontal systems, and hence nowcasting is also enhanced by these systems in those regions. However, in the tropics, quite challenging, and these regions are also the regions with poor logistics, you know, to monitor these dynamics. So how therefore can nowcasting, which heavily depends on such logistics, be improved? Already you said that satellite systems are used, so they are available over Africa, but it is underutilized. Areas where these logistics are lacking, can you really throw much light into these, you know, the comment whereby you said is underutilized? I know definitely maintenance is challenging. I think there should be something done much into this kind of challenge, because it's more of like a related issue globally. So if we are able to improve much upon our these tropics, whereby we know the dynamics are really not easy to predict, these areas, how can we really develop and improve such challenges? Thank you.
In a situation where not only are the simulations that are available are generally lower resolution in the mid-latitudes, and also where quite often it's difficult to generate this type of forecast, nowcasting does become more important. But then we've got this issue where nowcasting, broadly speaking, across much of Africa, doesn't happen in any sort of automated way. It seems to be quite limited to manual techniques and to very specifically to aviation. And the underutilization of tools has really been kind of it was a bit of a big question at the beginning of the project, and we needed to understand why that was the case, because NWCSAP has been around. But if someone is trained in order to do a particular role, it tends to be quite a small number of people that are actually able to do it. And so if you lose people, then you don't have the critical mass to necessarily continue doing something. And so in that way, you have got a solution to this problem in the kind of forecasting in general sense of using kind of the Puma synergy systems, which are generally quite easy to use. They're quite easy to teach other people how to use, and it manages the whole kind of data stream from the UMetcast system. On kind of updates of the system, lots of people are trained, and there's large amounts of money spent on making sure that there are a large number of people trained in the use of these systems, and they become very, very important. The issue is this whole kind of data management system that is taking the data from the dish and it's processing it, it's moving it around, and it's putting it in a format and then it's used within Synergy software for forecasting. It means that it's a black box. There is very few people generally, I'm not just talking about in the Met Service, that understand what is going on inside that box and how to access the data once it's hit. And one of the things we've really struggled with is kind of the allowing that data to come out of the system. So all you really need is for the UMetcast data to be split or to be accessible from computer stations, and then that can be processed, and we can do nowcasting processing based on that data that's available. This has been a real barrier, and myself and James Grove spent 2-3 days, I think, at GMAT in 2019, and we were able to actually have a look at one of these systems, and we had access to see where the files were going, and it was so complicated, but it is not an easy fix. And the issue is, these systems are updated every 5 or so years, and what if it all changes? And so if you've produced a solution to this to enable to access to the data from within the system and then process it to make your nowcasting predictions, if the system changes after that period, and then everything downstream doesn't work anymore, and it's one of the major problems we've come to, and it's not a lack of necessarily technical knowledge, it's an issue of having proprietary systems that there is not a lot of information out there about how they work.
I think you have to
How to work with them in that way. All the information that's available generally is how to use the system. I understand why that is the case, because you want people to know how to use the system in order to produce the forecasts. When that system is limited to being able to provide information that's useful for synoptic forecasting and very limited nowcasting, then where's the scope for improving the nowcasting that happens? I think it's really difficult to make those changes when there is such a reliance on those types of systems, but I understand why that is the case. I'm sorry, I might have gone off topic there. Did that answer your question?
Okay.
All right.
Lauren, please.
We've gotten another question from Osman Bayon from 9met. He's saying, using the automated forward extrapolation, to what extent can the image be moved forward while guaranteeing accuracy in terms of location and impact?
So that depends on lots of different things. So with high steps, so that is a different forward extrapolation technique to the one that's included within the VCSAT, but it produces similar results. There's been a bit of verification between the two, so we understand that over Africa we can be fairly certain that they're doing a similar job. What we tend to see is that skill does decrease with time, as you'd expect, and that there are limitations to how long you should be able to push that into the future. And actually, NWCSAT, I think the guidance in the information for using it is like 60 minutes. But we operationally push our extrapolation out to 90 minutes. And actually, I think it will be useful out to several hours. The problem comes if you've got particular times of day. So if you've got your period of the day where you've got lots of initiation events, your extrapolation will see that there's all these different storms dotted around the region that you're interested in, and it will not get rid of any of them. They will all persist throughout your entire extrapolation period. And obviously for the next 15-minute step, you produce another extrapolation period. So it only takes until the storms start disappearing for them to disappear from your extrapolations. But during that period of time, you don't know what's going on, and actually your skill drops significantly when there's lots of storms occurring. And the other thing is the extrapolation won't ever dissipate any storm. All it's doing is taking that image and moving it forward in time, and so storms aren't able to dissipate. So in that respect, if you've got a mesoscale convective system that you think is heading towards a high value target that you're concerned about, you can give an estimation of how long it's going to take to get there, and the severity, whether the rainfall is going to be the same as what it's suggested it already is. But there's no way of knowing whether that is going to continue. It might dissipate before it reaches the location you care about. And this is why we see that nowcasting kind of line on that graph drops so rapidly, because you start off with an observation. As you extrapolate with it forward in time, the scale drops very quickly because there's lots of chaotic things that happen in the atmosphere that you can't possibly hope to represent with a simple extrapolation. But it's still a really useful tool. And actually being able to see an animation of things, actually the forecaster looking at it will have a real intuitive feel about whether or not that is something that they should be concerned about. And I think that is one of the key things actually. In nowcasting systems, you need a human looking at it, someone skilled at forecasting to be able to say, I'm going to make a judgment call on this, and I'm going to say that this is something we need to be worried about. And yeah, the automated element of it can't do that, not yet at least. So yeah, we do know that skill drops off, but I still think even with that, it's a very useful tool.
James Wilson, can you please ask a question?
Yes, thanks, Alexander. Nice clear picture of what SWIFT is doing in Africa. Kind of wanted to know that. I have actually two comments. The first is, you know, there's so much confusion around the world about what really is nowcasting. And the extrapolation of satellite data usually is not really nowcasting because it does not give the detail that really qualifies for nowcasting.
Hey, really?
And I think you're very aware of that. My second point was I worry a little bit about the use of nowcasting for aviation. Of course, one of the biggest problems with aviation through the years has been the crashes from wind shear on takeoff and landing. And there is no way that you're going to be able to provide that sort of detail. So there's just a couple. I worry a lot about some of the uses of the term nowcasting. Just a comment.
So, yeah, the issue is, I suppose, realistically for Africa, there isn't an alternative for using satellite data and forward extrapolation of satellite data. And what we're trying to do, I suppose, is to apply the kind of techniques that you would use with rainfall radar data to regions that don't have access to that data, largely. I think also, so even though there is a radar network in South Africa, they still use NWC stuff and forward extrapolation of satellite data in that way, because it is useful for them in producing their nowcasts. Yeah, I agree absolutely. Like, if there were a greater detail that we had access to in terms of being able
see Michael's comment,
giving information about location of convective downdrafts and things for shear at airports, I thought that would be great, but I can't see from the satellite data you necessarily get that information a lot of the time. Partly because you're limited by the scale, like the pixel size of what things that you're looking at, but also because cloud cover becomes a major issue. But we have to work with what we've got, I suppose.
Brian Golden, your hand is up.
Hi, yes. A very interesting talk, and thanks for taking nowcasting into Africa in a sense, because it's a really important part of the suite of tools that you need for forecasting. On this issue of scale, I think designing the system for what you want to do with it is tremendously important. And I mean, personally, I would say that the way we used to predict mid-latitude depressions by extrapolating the movement of a pressure field was nowcasting, and that works fine for a day or so ahead. if you come down to the individual storm cell, you're only going to get an hour's predictability wherever you are, unless you happen to have a supercell. And I think what you're primarily aiming at is the mesoscale system in between. And in that case, you do get more predictability. I just wonder whether I mean, most nowcasting systems these days use the NWP data to give them the projection of the intensity, if you like. So you can get rid of systems, you can create systems if you use the NWP carefully enough. And STEPS, of course, was designed specifically to do that. So are you assuming that that's not going to be possible in Africa, or do you look at that as a future development?
No, I do look at that as a possible future development. I think it's probably beyond the scope of SWIFT. And actually a lot of what we've been doing in SWIFT for nowcasting is trying to utilise the things that are already available. NWCSAP as a tool does use NWP data to kind of augment the satellite data. So to a certain extent that is included there, but in terms of extrapolation there's been no kind of introduction of new cells or anything. One of the interesting things you said before about kind of predictability is, so we've been looking at the systems across Africa for kind of convective systems that would be producing intense weather, and seeing how far you can kind of do the extrapolations forward in time. And actually, in terms of useful skill, so it's kind of measures of kind of hit rate and skill score and fractional skill score and things like that. Actually, you can push this in certain parts of Africa for quite a long time if you pick the right time of day to start your extrapolations from. And essentially, if you avoid this initiation period where you've got rapid growth and you've got lots of cells that some of them are going to grow into much larger systems, others are going to dissipate fairly quickly, and actually you take it from a point when you've got mature mesoscale convective systems, you can get predictability that is useful out to about 4 to 6 hours. And actually, the distances that those storms travel in that time is fairly significant and would allow you to produce warnings and for people to take action. The other thing that some of my work is looking at is how simple can you make it, and basically looking at what is a suitable lead time, and all you do is identify every single cell that you're interested in, look at where it's been over the past however long you've got images for, and then just create a vector based on that. Is that still useful? And actually, from the preliminary stuff that I've worked on so far, that suggests that it can be quite good, surprisingly good, especially in regions like West Africa, where you've got a climatic setup that has got a very strong kind of guidance of these convective systems in terms of the direction of propagation and speed of propagation in kind of the low-level jet. And kind of that shear structure is fairly robust and it doesn't change significantly within the space of a few hours. So actually, even very simple techniques can be very useful, and you can produce forecasts for several hours that are reasonable and you would find usable as products. I think that is different in different regions, and that is the work that I need to kind of work on now. But no, I think, so the other thing I was going to say is, in terms of different products that are available, is NWCSAP does have the extrapolated imagery product that I think uses a combination of cloud motion vectors and movement of features in time from previous images, and also uses NWP data to produce its kind of vector field for its modification of the images that you've got currently. PySteps uses a simpler approach, I think, which kind of is basic optical flow, where all you're doing is taking images from the previous few time steps seeing how they change with time, creating a vector field, and just applying that. And actually, they come up with fairly similar answers. I think NWC stuff is better on the very short term, and then they kind of converge, and PySteps is actually slightly better if they're going out to kind of 6 hours or so. So it is an interesting kind of way of looking at it. I think any of these techniques would be preferential to none of these techniques. And that's really what we're looking at the moment in Africa.
Thank you very much. Miss Maureen, can you ask your questions? Can you read the chat, Maureen?
Yeah, so from the chat, that's Michael Baird. We say, thanks, Alex. Factors such as moisture availability, the shear vector, the African easterly jet can be considered in the forward extrapolation of storms. Although this might make it more complicated, it could help in increasing the scale at longer lead time. Then we also have another comment and chat from Ibrahim from Nigeria. So thank you, Dr. Roberts. I really enjoyed your presentation. Very educative and informative. 2 questions I have. 1, please, what do I need to do as to get faster alert when issued? What happens after the project ends in terms of continuity of getting the imageries and so on?
So, yeah, as I mentioned before, I feel like the inclusion of features such as the African easterly jet and kind of shear profiles and things like that, I think would certainly improve scale, or at least it has the potential to. I think that's beyond the scope of the project at the moment, but there hopefully will be continued nowcasting work going on after Swift. And we need to interpret it in Leeds, at least. And yeah, I think that there's definitely a lot of scope there for improving how long you can push these extrapolations for and how useful they'd be, and actually including some dynamical understanding of this would be the obvious next step. In terms of faster alerts, these are the plan for faster in terms of the API is to allow data to be made available in GeoJSON format and also as TIFF tiles or convective rainfall rate and the ODT products. And I don't think these are publicly available yet, but the project I think is going to make them available before the test bed in September. That is a latest deadline because we plan on using them for the test bed. And FASTER is actually a spin-off from SWIFT, but it's also partly funded by the university with the idea that this could become an ongoing commercial approach to actually producing this. And so we're going through processes at the moment and working out the legal situation with that and seeing if we can produce these products to be made available like long term, so well beyond the end of the project. In terms of the images that are available on the Swift catalogue, they will certainly continue till the end of the project, and because this catalogue and most of the processing hardware and software has been set up with someone that is a full-time employee of NCAST in Leeds, the hope is there that that will continue to be maintained as well. Obviously, I can't make any promises, but that is the plan.
We have 2 last questions, then we'll take a group picture. Prof. Amokuzi, your question? Hello, Prof. Okay. Okay. Is Xavier Calbert, can you ask your question?
Yes, hello. Just to congratulate you for the work. Xavier Calbert from the Nowcasting staff, as you know. And thank you for the very nice presentation, very nice work that you're doing. And I think this long-term thinking that you're doing, I think it's very, very, very useful. And I think this is the way to go, actually, because otherwise, as you said before, this has to, as some of your colleagues said, hopefully we should leave a legacy there that will be useful for future generations. So thank you very much for that.
Thank you.
We take a group picture, group photograph. So,
Hello, Russ. Hello.
yes, Maureen.
Yeah, I think there's one last chat message that's from Ikena. It says, thank you, Alex. Please, how close to real time can NWC SWIFT be updated?
So our experience has been that the images that we receive from our dish have, I think, a latency of about 15 minutes on arrival. So this is the raw data format, and then there is a processing step that needs to be done. So we've got it down to about half an hour for the latency, which I think possibly we could improve on a little bit, but actually it's pretty good. Like initially it was 45 minutes was our latency, and now it's down to about 30 minutes. But hopefully there'll be improvements in the future too.
So can we now put on our cameras for a group photograph? Samuel, can you take the photograph? Samuel?
Yeah, we're taking it. Yeah, it seems some people have not put on theirs. Yeah, it seems some people have not put on their camera. All right.
Take it anyway.
Yeah, I'm taking it anyway. All right. Thank you very much. Taking. Yeah, Bashir, I'm done. Bashir, I'm done.
Okay, please, Prof. Lamti, can you wrap up the meeting so we can? Prof. Lamti.
Yeah. I was muted. Thank you, Alex, for the nice presentation, and thank you, everyone, for attending. I think that the seminar should not be just a seminar for a seminar's sake. We are learning, and this learning must be put into practice. The interesting thing about SWIFT, which I like so much, is the involvement of both the operational centers and the universities. Because for me, as far as some of these things are concerned, if you want sustainability, you involve the universities. And it's an opportunity to improve the extent to which we are already working. Because there are many issues. Some of the questions coming up here are research questions, which you can pass on to the university people to do. And then the operational centers will test them before it becomes operational. So there are exciting things that can be done. Another thing that comes to mind is what Alex mentioned, critical mass. I myself started at the operational center, and it's very key. Critical mass is very key at operational centers. I think that knowing about the problem implies that you should do something about it. We shouldn't sit down and keep repeating the problem or keep saying this is a problem and not do anything about it. I think we have to do something about it. It doesn't always have to come from management level. Even at the operational level, when you are doing something, there will be young people who will be interested. You have colleagues who are interested. Involve them informally, so that even if it's not official, involve them. If you should leave the institution now, they'll show up. So if somebody there do the way. So please, let's take it at that level. And then, the other thing I like about SWIFT, about Nowcasting being introduced, is like what Brian Gordon said. It's part of the suite of tools that is needed for forecasting. one other one which has been introduced is the S2S. So for me, I'm very excited about nowcasting and S2S because of what Brian is. Alex made a statement which I found very interesting. He said, having any of these tools is better than having nothing. For example, if a ferry for inland water transport, we are aware of the accidents that occur over the lakes. If a ferry is about to leave, and in an hour's time a warning comes that this storm is expected in an hour, that ferry will not leave, so lives will be saved. So it is still useful, So we are very grateful for this and look forward to that. And I think Image, are very passionate since and learning and sharing ideas, but more so, let's have our own way of sustainability. The SWIFT project is unique. It's asking for sustainable plans and things like that. But those plans can just be paperwork if the people on the ground are not doing anything or not interested. You have to go beyond those plans or project development.
Thank you very much.
Thank you. Yeah.
Long time.
Yes, long time.
Thank you all for coming.